Video, we are going to learn how to use a graphical technique to solve an integer linear optimization problem. Imagine you are the owner of this peg manufacturing company that builds two types of pegs, and you got a last minute order from a customer that you cannot say no to. Yeah. And you want to make as minimum of these two pegs as possible to satisfy this customer, and you have a set of constraints. The first constraint is that you have to make sure that you make enough money from this order, which is you at least want to make $15 of profits. And you know that if you build the first peg, this type of peg, you would lose $8 in profit. If you build the second peg, you would make $10 in profit, let's say. Hypothetical scenario. Similarly, you have another constraint. There are some regulations, let's say, that require that you can reduce tax liability by $4 if you build the first peg, and you increase tax liability by $4 if you build the second peg. And you can build as many of these pegs as long as the total tax liability is less than or equal to 1. Yeah. So these are two hypothetical constraints. Some profit maximization that there's a lower bound of at least 15, and there's um, an upper bound of less than or equal to 1 for how much should be the difference or should be the total tax liability. Yeah. And you have a goal. In this case, you either have a goal to maximize or minimize. And here you're trying to find the least amount. So you're trying to minimize. Yeah. So very quickly, you need to understand how to parse out the business scenario and be able to convert the business scenario into a mathematical model that tells you what are you trying to do? What's your goal? Is it to maximize or is it to minimize? What are the variables that you need to make decisions on? Yeah. In this case, it's how many of these pegs you would build and what are the constraints. Yeah. And that's about it. If you can parse those things out, then you are able to quickly convert this large text into a business problem that can be mathematically translated to Excel. So let's imagine that we would have x1 be the variable that says this is the amount of pegs we'll build for the first item, and x2 is the number of pegs that we'll build for the second item. So we'll have two variables. So finding out what are your decision variables, in this case there are two. There could be many. When there are two, you can easily solve this graphically in a two-dimensional plane on a piece of paper or on this device. But when it becomes multiple variables, then it becomes harder because it's n-dimensional to solve that. Yeah. So we have two variables, and we are able to find out quickly that we need to decide how many of these two items to build, so x1 and x2. So we identified the variables. We also have the objective, which is we want to get as minimum number of quantities of these to be built, x1 plus x2. We want to minimize that, yeah? Minimize the total order size. And you have some constraints. In this case, you have two. You want the profits to be at least greater than or equal to 15, and tax liability of both of them to be less than or equal to 1. And we are given how much each of these items increases or decreases your tax liability or profits. And finally, we cannot build 1.2 of x1, so we have integer constraints, and we have to build positive number, at least 0 or more. We cannot build negative quantities of each of these items. So that is the second step. First step, really deeply understand the business scenario, find out all of the decision variables that exist, and then convert the business scenario into a mathematical model. So now we have converted this into a mathematical model with constraints, the objective, our goal, the decisions we're trying to make, and then this can be fed directly into Excel solver to solve this. But we're going to solve it manually using a graphical technique. Yeah. So how do we do this? The first step is to find out and plot each of these constraints one by one. Yeah. So if we can form this equation, we can now try to plot this line. This is an equation of line. How do we do that? We were going to plot on x-axis variable x1, on y-axis variable x2, and we are going to now plot this first constraint, minus 4x1 plus 4x2 equals 1. I've just said equals 1 bear with me, it is less than or equal to 1 is what we want, but we'll add the less than or equal to. So we take the first constraint and then we find out how do we draw this line and also incorporate this constraint. So given there are two variables, we can draw this on a piece of paper. So we put the first variable on x-axis, the second variable on the y-axis. Having done this, we need to find out 2 points that actually are on this line. Yeah, once we know 2 points, we can build a line. So we can do this. Assume x1 equals 0. Put x1 equals 0 in this equation. You get 4x2 equals 1. And then so when we put x1 equals 0, we get x2 equals 0.25. Similarly, when we put x1 equals 1, we get x2 equals 1.25 in this equation. So by just assuming two different values of x1, which is 0 and 1, we can get two different values of x2. So now we got 2 points, 0, 0.25, 1, 1.25. When we have 2 points, we can easily draw a line. So we have this line here, this is 0, 0, this is 0, 0.25, and then 1, 1.25. So when we have these 2 points, we can easily draw this entire red line that connects, yeah? So when we have these 2 points, we connect these 2 points and then draw the line. So that's the equation of the line, which is minus 4x1 plus 4x2 equals 1. But now remember, we want to incorporate this less than or equal to, yeah? So that'll give us this shaded area. How did we get to this shaded area? This shaded area is also called the feasible region, which basically says if we were to draw and incorporate this constraint, minus 4x1 plus 4x2 less than or equal to 1, then we are able to get to this shaded area. It could be here on this side or this side. But how do we know which side it is? What side is the feasible region, or what side is possible? And what does this imply? The way we do that is we substitute 0, 0, which is we use value x1 equals 0 and x2 equals 0, and then we look at whether 0, 0 satisfies this inequality. So we substitute x1 is equal to 0, x2 equals 0. So then we get 0 less than or equal to 1. Is 0 less than or equal to 1? Yes. That means 0 satisfies this inequality, meaning 0 is on the feasible region. If what you get here is doesn't satisfy the inequality, or 0, 0 doesn't satisfy the inequality, meaning 0 is not in the feasible region. In this case, 0, 0 satisfies this inequality, meaning 0, 0 is wherever 0, 0 is, that is where your feasible region is. So we know 0, 0 is somewhere here. So that means the feasible region is this side of the line. So we are able to shade all of this as the feasible region. Yeah. Find out where 0, 0 lies, and if 0, 0 satisfies the inequality, that wherever your 0, 0 is point, wherever your 0, 0 point is, that is the side on which the feasible region lies. Yeah. So now we are able to plot this feasible region. If we can do this for one of the first, this is the first constraint, remember, and the tax liability constraint. Now we're going to add the second line, which is the profit, which is minus 8x1 plus 10x2 greater than or equal to 15. So we can do the same thing. Find out two values for x1 equals 0, x1 equals 1, 2 points. And then you will get this equation of this line. And then find out, is 0 greater than 15? No, meaning 0 is not in the feasible region. That means it's whichever place the other side is the feasible region. So now we have this as the feasible region for this constraint. So we got the first feasible region on the right-hand side, and then now we have the other feasible region on the left-hand side. Now we need to combine the two. And once we combine the two, we get one area that goes to the bottom of this blue line, and the other goes to the top of this yellow line. And so we have this combined area which satisfies both. Yeah, this top of this yellow line, bottom of this blue line. So this is now our feasible region. Yeah. So for these two constraints, now we have a feasible region that is common in both, meaning it's also satisfying the blue line and the yellow line. And where they intersect is one of the corner points. Yeah. So here we have 6.25 and 6.5 is where these two equations or these two lines intersect. If you solve for these two equations, two variables, two unknowns, and two equations, two unknowns, you can actually get this intersection point. So 6.25, 6.5 is the minimum point. So this is actually the optimum solution if you do an LP relaxation for integer, meaning if you remove the integer constraint, the optimal solution would be 6.25 of x1 and 6.5 of x2 is what you should build. But no customer will accept 6.25 of an item. They'll either accept 6 or 7. So what you also need to do is remember, you need to add the non-negativity constraint, meaning all of this area is not useful. Anyways, our feasible regions here. So we will add the x1 greater than or equal to 1, so which is this line, and x2 greater than or equal to 0 and x1 greater than or equal to 0. Yeah, so we added these two lines as well. And we are able to get an optimum solution with linear optimization with LP relaxation. But now if you want to add an integer constraint, meaning we don't want this answer, we want a whole number, yeah, because that's what will tell us what's the minimum number of items we can build. So what we then need to do is find out all of the points and that are in this shaded area that are whole numbers, yeah. And so there are various algorithms. Branch and bound is one such technique, algorithm to use. And with that, what you can do is you can get all of these points. So you can get 8, 8, 9, 9, 10, 10, and so on and so forth. But remember, our goal is to minimize. So if 8, 8 is the lowest, then that's where we will have the minimum value if we substitute that in x1 plus x2, yeah? So remember, always rounding is not the best way. Rounding up and rounding down or mixed rounding is not the best way. Substitute the values that you get of all of these integer feasible points into your optimization function and find out which one gives you the minimum value, in this case, of the objective. So 8 and 8 gives you the minimum. So now with that, the shaded area is no longer our feasible region, but these black dots, which are integer, are our feasible region points. And so now we found out an optimum solution 8, 8 for that satisfies what we are looking for, meaning build 8 of pegs x1 and 8 units of peg x2. So this is how you're able to plot on an xy plane two variables and then build all of these constraints. You could have several other constraints. I have 4 constraints, x1 greater than 0, x2 greater than 0, and these 2 constraints, but you could have as many constraints as possible. So you have to keep checking which of these areas are common across all of these constraints, yeah? And that's how you keep getting to a solution of finding out where the optimum solution is, yeah? All right, thanks.